Hi everyone, my name is Andrew. I'm a student at the U of I, and I was just going to go over some trigonometric concepts and practice problems. So let's get started. I'll start with a quick overview. The problems we'll be doing will involve using U-Sub, Trig Sub, and also integration by parts. And these are, different techniques that'll help us integrate slightly more complicated functions. I guess another quick overview about integrals and integration. So here's the integral, and an integral is actually very closely related to sigma notation. I guess the only difference would be, like for sigma notation, you start at I, or you start at 0, and then you have I. I can be 1, 2, 3, it can be whatever, and then you go up until n, so it can be like 5, 20, it can be anything, any integer k. Whereas integrals, it's like an infinite sum. So you have two bounds, and then a and b, and then you have an infinite summation. That's what the dx is. So here in sigma you sum f of x. But here you sub f of x dx, and this dx is an infinitely small iteration of f of x. So it's like I, but like infinitely small, and b goes to whatever b is. But the point is, integrals are basically infinite sums. So anyway, let's just get started with one of our first problems. Let's do this. Let's start simple with maybe t e to the 6t dt. Now, if you've never seen a problem like this before, and I'm assuming you're familiar with all the concepts I just talked about, then honestly, I think it's good just to take a moment to look at it. And the first thing I look at when I see a t, I see an e to the 6t. These are two different sections, or parts, whatever you want to call it. Parts. Integration by parts. That's my first thought. So the next thought, after deciding I'm going to use integration by parts, is deciding what's going to be the u and what's going to be the dv. Because we have to choose one of these terms to find the derivative of, and the other one of the terms to find the antiderivative of. So this is all stuff you'll get very quick at, but if I look at t, if I find the derivative, that's just going to be 1. If I find the antiderivative, that's going to be t squared over 2. If I look at e to the 6t, if I find the derivative, I think it's just going to be e to the 6t over 6. If I find the antiderivative, it's going to be e to the 6t over 6. So in both cases, the complexity is very similar. Let me just double check this. Oh, I'm sorry, it's not. I just want to double check that. But anyways, the complexity is very similar because you factor out the 1/6 or the 6, and you get the term e to the 6t. So this, we're not going to consider this. We're just going to look at what makes this term simpler. And in this case, making this simpler will be finding the derivative of t instead of the antiderivative. So that means we're going to make u our t. Our t our u. And then our dv is going to be e to the 6t. Alright, so now we find the derivative. That's just going to be 1, so it's 1 dt. And then v, it's going to be the antiderivative e to the 6t. And that's just going to be e to the 6t over 6. Not 6e to the 6t, as I wrote. Yeah, now I'll just write out the formula for integration by parts. And it's very simple. And I can go over how they did it, but it really is just like the chain rule. If you take the chain rule and you have two functions, you simplify it, move some stuff around, you're going to get this. In this case, u and v are going to be two different functions, right? Okay. So now we just plug all this stuff straight in. We do t e to the 6t minus the integral of e to the 6t over 6 dt. Now this is really straightforward to simplify. Minus 1 over 6 e to the 6t dt, and we already found the antiderivative of this. So it's t to the 6t, it's a bad t, minus 1 over 6 times e to the 6t over 6. And then can't forget the plus c, because that plus c is very important to note when we're finding antiderivatives. There we go. That's just this but simplified. And so that's how you do integration by parts. That's a very basic example. So now I guess we can go into some slightly more complicated examples of integration by parts. Let's try this. Let's do the integral, and we'll have x squared plus 8x times cosine x dx. All right. Now, we know we're going to be using integration by parts here. If you don't know that beforehand, again, just look at, you have two terms here, and it's not a rational function, so there's no like degree difference. So like this term isn't 1 degree away from this one. So not U sub. We only have one trig function here, so don't try to do tricks up here. Let's just do integration by parts. And again, we have to find which term we make our derivative will make it simpler, and which term we make our antiderivative will make it simpler. So if we just, I guess we can practice getting faster at this. X squared plus 8x, the derivative is 2x plus 8, antiderivative x cubed over 3 plus, what's that, 4x squared. Very, very, very much more complex to find the antiderivative. Cosine, we know it's either going to be negative sine x or sine x. Right? So again, don't really consider this because the complexity is basically the same. So that means we look at this and we're going to say, okay, 2x plus 8 is a lot simpler. Our u is going to be x squared plus 8x, and our dv is going to be cosine x. So v is going to equal sine x, and du is going to be 2x plus 8. And you can't forget this dx here. This dx is very important. It's very important when it comes to substituting everything in. So we're just going to write x squared plus 8x times sine x. Right, it all goes back into the formula. And this is the formula uv minus v du. 2x plus 8 dx. All right. Now, this is something that you might be able to think about like before you even start the problem. But you can see here that after we've simplified this a bit, this is still not a very clean formula or function. We can't, there's two parts, can't antiderive this very easily. But we can just use integration by parts again, actually. It's the same thing. What makes everything simpler? 2x plus 8 and sine x. So the antiderivative is going to be negative cosine x. And du is going to be 2 dx. And the way this works when you do integration by parts is just think about like this. This turned into this. So that means that when we integrate this by parts again, we're going to leave this from part out here alone. 8x times sine x. We'll keep the minus. And then you can just think of it like a big parentheses, right? This goes to this, so now this is going to go to this. And then uv, so that's 2x plus 8 times negative cosine x minus integral of v du in parentheses. Cool. So hopefully that makes sense. I'm just going to keep simplifying here because we basically did all the heavy lifting for this problem already. 2x plus 8 times negative cosine x, and then plus 2 times cosine x dx equals x squared plus 8x. And it is tedious to write out all this algebra, but I do heavily recommend doing it, because with slightly complicated problems like this, and problems that will get even more complicated in the future when you pursue math, it's good to write out all the steps, so you can, if you do end up making a mistake, you can see where you made that mistake, and it takes away a lot of stress in your life. So let's just do plus 2x plus 8 times cosine x minus 2 sine x plus c. And then that's basically the answer for that. I don't know what I'm looking up. Yeah. So now let's go back. Let's do a third one. Let's see. This isn't slightly more complicated. I think it's actually less complicated than number 2. But what it'll do is it'll challenge how we think about making our u's and our dv's. Alright, so the first one was just an intro to integration by parts. The second one, we had to integrate by parts twice. And you might have to do it more than twice, I don't know. But just an example that's modular. Here, we need to decide carefully what our u is going to be and what our dv is going to be. Because here's where it gets tricky. Is, if you look at it, ln of t. The derivative of ln of t, let's write the derivative up here, is going to be 1 over t. And the antiderivative, I think, let's double check, it's like ln of t times t minus t. And that is very, very much worse. But if you look at t to the 4, finding the derivative is 4t cubed, and finding the antiderivative is t to the 5th over 5. Now, I guess it's not too hard of a choice to see which one we should choose, but the point is to not be distracted by powers like this, because usually the goal is to get rid of these higher exponents, but in this case we are going to have to get the exponent higher just for the sake of getting 1 over t instead of this ugly mess. So we'll say ln of t is our u, and our du is going to be 1 over t dt. And our dv is going to be t to the 4, and our v is going to be t to the 5 over 5. Cool? Okay. Alright, you don't have to write out the formula every time. I didn't write it out for the last one, but it's never a bad idea just to rewrite it. Just for the sake of getting everything right, and if it's a high-stress situation like a test, then it might not be a bad idea. But anyways, do it however you want. There we go. And now this basically is the heavy lifting of integration by parts, I'll be honest. Deciding what the u and the uv is, that's honestly the tricky part. And unfortunately the part that may take a certain level of intuition for more complicated problems. But we'll factor out the 1/5 and we'll cancel out these t's, so we have t to the 4th. So it's going to be t to the 4 dt. And this makes it really simple, so ln of t times t to the 5th over 5 minus 1/5 t to the 5 over 5 plus c. And it's always nice to write it as simple as possible. But yeah, cool. Just another simple integration by parts problem. Let's jump into another one. Let's try this. We're going to do integral, and we're going to say sine 5, let's do a fun variable, a, cosine 8a dA. And this is just to highlight, these are just variables, a, x, y, z, just use whatever variable you want. Now here is another case where you have to decide what our u is going to be and what our dv is going to be. In this case, it usually makes sense to make our u the term with the higher exponent. And The other thing to note that goes hand in hand with this is if you have sine functions and cosine functions, when you substitute in, actually, I'm sorry, we're not going to use U-sub. I mistook this for U-Substitution. We're not going to use integration by parts. You might look at this and say, okay, I have two terms, integrate by parts. But finding the antiderivative of any one of these is not going to be fun. It's you can, sure, but there's a much better way to do this, and that's U-sub. And the way to decide what your U is going to be is looking at which one has the higher degree. The other thing to note is when you have cosine and sine functions, when you make one of them U, one of these is going to switch. So you're going to have du equals negative sine dA, whatever this is. But that means that dA, which is right here, is going to be du over negative sine x, which means we're going to be able to take 1 degree away from the other term over here. And then same for sine. So if we make u our sine, so du equals cosine dA, and that means dA equals du over cosine, and we'll be able to take 1 away from cosine, the cosine term. Same will be true if you have like a fraction or something. But yeah. Anyways, I'll just get to working away on this. There. So that should make sense. Now we just start by plugging everything back in. So here's actually the other tricky thing. This is a slightly more complicated problem because then we have sine to the 5a times u to the 8, and then dA is going to be du over negative sine a. So we'll write that du over negative sine a. One of these will cancel out, one of those will cancel out, and we'll take the negative to the front, so we'll have negative integral sine 4a u to the 8 du. We still have this sine 4a. So how do we get rid of that? Well, usually what we do is we just relate sine, or whatever term we have left, to be in terms of u. And we can do that using our trigonometric identities. So we have sine square x plus cosine square x equals 1 as one of our trigonometric identities. Noticing that this is an even power, we can write sine square x equals 1 minus cosine square x. And so now, if we rewrite this out, sine square a u to the 8 du. Now we can write this in terms of u, because u is equal to cosine a. So if we write this as a minus cosine square a. And that's how we handle u-sub with terms that are still left over after substituting. So write 1 minus u squared times 1 minus u squared times u to the 8 du. Okay, and now we just FOIL this out. We have negative integral, and that's going to be 1 minus 2u squared plus u to the 4th times u to the 8 du. And just keep simplifying, distribute. And then here it's very simple to find the antiderivative. It's just u to the 9 over 9 minus 2u11 over 11 plus u to the 13 plus c. And then of course you have to substitute the u back in down here. So it's going to be negative cosine to the 9a over 9 minus 2 cosine to 11a over 11 plus cosine to the 13 15 plus c. There you go. And you can distribute the negative 1 if you want, but that's how that will go. Let's try something similar, I guess. Let's do a fifth problem. How should we do this? Let's just have tangent to the 6th of b times cosine to the 7 of b times dx. And again, here we will try and use U-sub, but another thing that's good to note is when you have an equation, really try and simplify it before you even get started, because a lot of the times you'll have a problem either on a test or in real life where you'll have functions or terms that can already be simplified before you even get started doing your work. And here's how we're going to do it. Tangent is, sine x over cosine x. So raise it to a power. You have sine kx over cosine kx. Right? So that just means we have sine to the 6b over cosine to the 6b. Then we'll multiply that, by cosine to the 7b dx. All right, get rid of this. Turn this into 1. So now what we really have is sine to the 6b times cosine b dx. And now we can use U-sub. We can say u equals, again with the higher power, u equals sine b, so du equals cosine b db. And this should be b, I'm sorry, not dx. Muscle memory. Just because of the terms I'm using, should be b. Now db equals du over cosine b. So we're going to have u to the 6 times cosine b times, and then db is replaced with du over cosine b. These cancel out. We have integral u to the 6 du, and we can easily integrate this. It's u to the 7 over 7 plus c. So that's going to be sine to the 7th b over 7 plus c. Cool. So that's just another simple U-sub, but you have to simplify the term first before you get started. Let's go down to another one. Let's see, how should I write this one? Let's write it like this. Say we have constant out here, 10, and then we have tangent to the 3rd. Maybe it's a fun one, q times secant q dq. I guess here. This might be a question that they give you, okay? So again, with the whole, simplify everything before you even get started. And now we don't have to think about this 10 until the very end of the problem. So here, again, we're just going to try and use U-sub. So here's the interesting thing. Because we're dealing with secant and tangent here, and taking the derivatives of them will be different, it won't actually be ideal to take the derivative of the higher degree this time. Because if we take the derivative of tangent, we get secant squared. And that's only going to get rid of this one secant, but it's also going to leave another one in the denominator. But instead what we could do, we could say u equals secant q, and then du equals secant q tangent q. And why this is going to be better is because we have sorry, 2dq. Because we have a tangent and a secant right here. So we'll get rid of the secant, we'll get rid of another one tangent. So let me just start writing this. This will be 10 integral. And we'll actually split this up because it'll make more sense. So tangent squared q. Actually, put the square on this side. Tangent q, secant q, dq. So we're going to say that u equals secant q. But if we substitute u for secant q, we're not going to have secant anymore that we get rid of this with. Now we could write u equals secant q. You could just write u tangent q, and then this would be tangent u. Whatever. It's all the same thing. The point is, all of this is going to go away. And we're just going to be left with a u here and a du here. I'll show you. We have a 10, then we have tangent squared q, and then tangent q, secant q, times du over secant q, tangent q. This cancels out. So now we have 10 times the integral of tangent squared q times du. Well, again, we have a u here and a u here. This is obviously not in terms of u, so what the heck are we integrating? But we can make this in terms of u, and that's the whole point of using U-sub, is to make the leftover term in terms of u. And this is one of the trigonometric identities. All right? What is it? Tangent squared equals 1 minus secant squared q. That is a... Wait. This is not right. Tangent squared plus 1 secant squared, which means that it's going to be secant squared plus 1. Okay, sorry about that. That's better. So now we can write u in for secant. 10 integral u squared plus 1 du. There we go. So then 10 times u to the 3 over 3 plus u plus c, and that equals 10 times secant q cubed over 3 plus secant cubed plus c. And there we go. This one is definitely a bit tricky to handle at first, but definitely think about approaching it from different ways. And you might have to take multiple stabs at it too, but that's okay. Let's move on to another one now. Let's try and do one with trigonometric substitution. We're going to say x squared over square root, say 36 minus x squared dx. All right, now here's something important that you'll be consulting, or you should remember when you ever have to do trig substitution. I'll make a little table over here. And it's going to be a list of translations. There's 3 that you need to remember. When you have expressions that contain a squared minus x squared, where a is just any constant, you have a squared plus x squared, and you have x squared minus a squared. The translations you're gonna make. This is basically U-sub, okay? Trig sub is basically U-sub, but we're gonna use this table, okay? So then we're gonna say x equals a times sine theta, x equals a times tangent theta, and then here x equals a times secant theta. And I'll get into this as I do the problem, but the reason for these translations being so is because of the different trigonometric identities. So you're going to have sine square plus cosine square equals 1, and tangent square plus secant square, no, tangent square plus 1 equals secant squared. So maybe you can see it already, how these two will come into play with each other, but I'll show you in the problem. Just know that is where they come from. Just like how the integration by parts formula comes from like the chain rule, this trig sub will come from the trigonometric identities, and I'll get into it. But just for now, we're gonna practice identifying our a and identifying where we're gonna sub in x for. So looking at this equation, we have to find which one it matches to. Now, it shouldn't be pretty hard. Obviously, it matches to the first one because we're going to have a constant minus x squared, right? In this case, our constant is 36. So we're going to have 36 minus x squared equals a squared minus x squared, all right? That's what we're doing. And if you really want to solve this like algebraically, you can just say 36 equals a squared. So x does equal plus or minus 6, but we're just going to say, for the sake of this, it equals 6, okay? So we're going to say x equals 6 sine theta, and then following traditional U-sub procedure, I'm going to say dx is 6 cosine theta. So now let's start rewriting this in terms of this new thing. We're basically writing like with theta now, okay? So this should be d theta. And the reason it's going to be theta is because later in this problem or some other problems, we're going to have to use some right triangles. But yeah, we'll get into that. So if x equals 6 sine theta, that means x squared is going to be 36 sine squared theta all over square root of 36 minus 36 sine squared theta. And then dx is replaced by 6 cosine theta d theta. Alright, now if you've done it correctly up to this point, then this denominator will be really simple to simplify. And here's what I'm going to show you. We're going to have the square root of 36. Factor out the 36, you get 1 minus sine square theta. And this is the trigonometric identity. This is sine square plus cosine square equals 1. 1 minus sine square equals cosine squared. So that's why we used sine here. So now we can say the integral is 36 sine squared theta over, and then square root 36 is 6, times the square root of cosine squared theta. And obviously this should go here. Sorry, this should go here. I was lazy. So let's rewrite this. Let's say 36 sine squared theta over 6 cosine theta times 6 cosine theta d theta. Alright, so we cancel this out. That's going to be antiderivative of 36 sine square theta d theta. Cool. Now, I'll keep working on this, but just factor out the constant 36, and we have sine square theta d theta, and then this does get a little bit tricky because we have to antiderive this somehow. Now we're going to use some more trig identities. So we know sine square of theta equals 1 minus cosine square theta over 2, right? So we'll plug this in because this is a lot easier to solve. So 36 times 1 minus cosine square theta over 2 d theta. And then factor out the 1/2. So 36 times 1/2 is 18 times 1 minus cosine. Sorry, this is 2 theta. I don't know if that's clear. Wrote that bad. Okay. And now we can this is something we can antiderive as well. Just like we can antiderive sine 2 theta, we can antiderive cosine 2 theta. So 18 times antiderivative of 1 d theta is theta minus sine 2 theta over 2 and plus c. Okay, now it might look like we're done, but we aren't exactly done yet because we are writing with terms of theta, and we need to write with terms of x. So here's what we do. We go back up to here, to where we substituted in x, and so x equals 6 sine theta. X equals 6 sine theta. And that means that x over 6 is going to equal sine theta, and that theta equals arc sine x over 6. Yeah? Okay. So now, let's go over here. That equals 18, and then we'll simplify the first part. Arc sine x over 6, and then here's what the heck? Anyway, sine 2 theta over 2 plus c. Okay, so now we still have this theta up here in the sine 2 theta, and it is a bit weird. Let's see. But let's just keep writing this. 18 times arc sine x over 6 minus sine, and then 2 times arc sine x over 6 over 2. Wait, I forgot something. Here's what I forgot. I forgot the trigonometric identity, and that's sine 2 theta equals 2 sine x cosine, or 2 sine theta cosine theta. Okay. This is because putting sine 2 arc sine x over 6 is not great. Can't exactly do that. I mean, you can, but here we're just gonna use more trigonometric identities. Gonna be using them a lot, and fortunately I'm not the greatest with them, so that's my bad. But we'll keep writing this. 18 times arc sine x over 6 minus sine theta cosine theta plus c. All right, now this is something that we can do. All right, so now we just keep plugging in theta into here. So equals 18 times arc sine x over 6, and then sine of arc sine is just, it's not going to cancel out, so we have x over 6. And then here's where we have to draw our triangle, because we're trying to find cosine of theta, and we know what arc sine of theta is, so we can find cosine. All right, this is that. All right, but we need to find this side right here. So we just use Pythagorean theorem, and that's 36 minus square root 36 minus x squared. There you go. You might be able to do that in your head, but I just wanted to show the algebra for the sake of it. So cosine of theta here is going to be the opposite over, the adjacent over the hypotenuse. So it's going to be times square root 36 minus x squared over 6. And there we go. That's it. We'll simplify this a little bit as per good practice, but really we found the answer by now. And that's 36 minus x squared over 36 plus c. Awesome. Let's do one more. Is that number 7? Okay. Let's do an 8th one down here. We're gonna do another trig sub, but we're gonna use a different trigonometric equation. And we're gonna have a slightly more complicated a. All right, so right off the bat, we can tell that this is not a perfect square. It's very close to being a perfect square. It's 1 off of 9, but very much not a perfect square. But here's what we can do instead. If we remember the table, what we can look at is we have the expression here, x squared minus a squared, right? It's x squared minus a constant. You can honestly just think of this as a constant, but it is important to keep that square right there. And so the sub we're going to use is going to be x equals a secant theta. Now, this is where it is useful to do the algebraic, write algebraically like I did in the other problem. You don't have to. You can literally just see this and write, okay, square root of 8. But the way we get there is just take this out, take this out, take this out, take this out. A equals a squared. A is going to be square root of 8. Again, plus or minus, but just we're going to use positive here. Shouldn't matter. So a equals square root 8. That's what we're going to use. So x equals square root 8 secant theta. And then dx is going to be square root 8 secant theta tangent theta d theta. Awesome. Now let's just get to substituting. I think what I just had. Square root 8 secant theta over square root, and then we're going to have square root 8 secant theta squared minus 8. And then dx is going to be square root 8 secant theta tangent theta d theta. All right. Now let's work towards simplifying the denominator, which again, if we've done all this properly, it'll simplify very well. Looking at this, we're going to have 8 secant squared theta minus 8, and yes, it does simplify well. All right. I think my laptop fan is going crazy right now. Not too sure I like my current laptop. It's a bit small, and it bugs out a lot because I tried to be too fancy with the keyboard and the mouse pad, I'll be honest. But anyway, just remember secant squared theta minus 1 is going to be tangent squared theta as per the trigonometric identity. And again, that is why we used secant here instead of any other one, because we have secant squared minus 1, and that translates very well to tangent squared. So square root 8 secant squared over square root 8 square root tangent square theta. Here we go. Times square root 8 secant theta tangent theta d theta. Okay. And so then, I'm sorry, I am taking this every step, but I want to, in case anyone's confused, just show you how exactly everything is done. Right, square root of tangent squared is tangent, and then now we'll get to cancel out some stuff. So we'll cancel out this tangent, and this is square root 8 because that's down here. And so then what we're going to have is square root of 8 secant square theta d theta. Okay, and we factor out square root 8 integral secant square theta d theta. That's just tangent. So square root 8 tangent theta plus c. And again, we can't leave this theta here. So we recall that we subbed x in for 8 square root 8 secant theta. And so x over square root 8 actually, wait, let me redo this. X equals square root 8 times 1 over cosine theta. This will make things a lot better. 1 over cosine theta. So x cosine theta equals square root 8, and so cosine theta equals square root 8 over x. So theta equals our cosine square root 8 over x. All right, now we'll just write this out. So we have theta here, so the adjacent, square root of 8 over x. And now we're trying to find the side here because we want to find tangent of theta. So b squared plus 8 equals x squared. B squared equals x squared minus 8. Sorry, square root. There we go. Square root x squared minus 8. There we go. And so that's really all we do. Square root 8 times, what is it? X squared minus 8 over square root 8 plus c. These cancel out. So then our answer is just x squared minus 8 plus c. Cool. That'll be all the problems I go over today. Hopefully those covered a lot of different concepts when it comes to simplifying slightly more difficult integration problems. But I'll definitely make more videos, and please, if I messed up or if you have any comments, questions, just leave them in the comments. I'll get to them. Yeah. Have a good day, and good luck studying.